Here is Buniy from Chapman University. He's here for the top program for the whole semester. And he's going to tell us about invariance for entangled states.
Thank you. Well, first of all, I would like to thank organizers, Keith and Tom, of course, for this great opportunity. And I'm just trying to see if, right, that's called full screen, I guess. That works. This is a little bit outside of the subject of many of your scientific interests, but nevertheless I will try to explain things, but don't be afraid by this number. We're not going to go all the way to 73. We probably cover 25 or something out of them. So what's this whole thing is about? Well, first of all, this is a report on two publications. These are two different articles in Journal of Physics A that we had with Tom. And this is an attempt to solve a long-standing problem, and we don't claim we solved it completely, long-standing problem in quantum mechanics, which is how do you classify entanglement? Well, we had this overview lecture a few days ago by Elliot Leib, and he mentioned he had made a nice introduction to what entanglement is, and I just remind you the basic fact is the following. If you have two quantum systems which are now in contact and they are interacting, and something happened with them, you have them close nearby, and then you push one system away, and he used the word moon, could be even further away, of course. But the main point is it has to be far away in order that there is no causal contact. So for instance, if you do some experiment here with the system A, so you had A and B and you pushed B away. If you do something with A, you want to observe something happening to it on a time scale less than there is a chance for information from system B to communicate back to us. In other ways, we can, by measuring A, we know what's happening with B, which looks like propagation of information with the speed higher the speed of light, and that was the problem that Einstein and Podolsky and Rosen had in their original paper in 1935, if I'm not mistaken by the year. So they used that paper, which actually introduced entanglement, as the way to say that quantum mechanics is wrong and validate quantum mechanics. Of course, the paper or the subject was dormant for like 20 years after that, and then interest reappeared, and with Bell and other people starting doing various things. Now, what I'm not going to talk about, what Leib talked about, which is entanglement entropy. This could be another subject. I work on that too. But just to differentiate between two things, if you have entangled state, you can calculate certain quantities, and one of them is entanglement entropy, which is 0 for pure state, disentangled state, and non-zero goes to plus infinity. It's positive definite for entangled. And the higher the entropy, the more entangled the state is. Now, question we asked ourselves is, could there be any other invariance? Could we have not continuous invariance, but discrete? You could have multiple continuous invariants. There is entanglement on formation. There are various other adjectives added to the word entanglement, and people study them, various properties like concavity, and etc. But what we attempted to do is to actually look at the discrete invariance. Why discrete? Well, it's actually a coincidence because we were looking from point of view of the subject that we're going to talk later on about, which is generalization of Aharonov-Bohm effect. And that thing is topological by its nature, and as you know, topology versus geometry is discrete versus continuous. So there is an underlying topology in all this stuff, but it's so simple topology that it actually makes sense to talk in terms of linear algebra alone. And everybody knows linear algebra. So let's start. So probably I already said many of these things. EPR, Einstein, Podolsky, Rosen, that was called paradox. And again, this phenomenon, entanglement, is not present in classical mechanics. There is no entanglement. It's only in quantum mechanics. And you don't need any interaction for entanglement to present itself. Now, it turns out that entanglement is nothing more than a consequence of two principles, fundamental quantum mechanical principles. First of all, superposition principle. In other words, if you have a state in you have one state, you have another one, then you can have a linear combination of two states. That's a superposition principle. And as we know, it works in mathematical terms in terms of Hilbert spaces. Now, tensor product postulates, that's the only remaining piece, is needed because we have two systems, or more than two systems, so you need to know how to create a wave function, how to create first space in which wave function lives, if you have a space for one party and space for another party. So you take tensor product of two spaces, 3, n, etc. So this quantum state of an n-party system is a n-product Hilbert space of corresponding Hilbert spaces. And let's just start slowly with two spaces, because that's a very important case to consider and to understand why the problem is so difficult for n greater than 2. So n will stand for number of spaces, number of tensor product of Hilbert spaces that we tensor together. So if you have two spaces, v1, v2, then the wave function lives in a combined space, v1 cross v2. And what we need to do, because this is quantum mechanics, we need to eliminate dependence on transformation of bases, because as we know, they have no physical significance. Choice of basis is immaterial. Therefore, we say that whatever quantities we derive, invariants, I will call them, and I will explain exactly what I mean and show how they look, should be invariant under certain transformations that belongs to some group. So these are the groups that map v1 space to v1 and v2 to v2. And as a consequence, tensor product, well, direct product of two spaces would be mapped by the product of two groups. But the very important point is to notice that transformations of a tensor product space is much larger, linear transformations, much larger than the space of products of two groups. So there's a big space G that transforms V, and G1 cross G2 is a very, very small subset of it. Subgroup of it. So in other words, you can rotate the whole system in such a way that you don't, if you take a cubic group, you rotate x, you rotate y, that's the only thing allowed. Of course, you can rotate little bit, but you cannot scramble the whole thing together, because then you won't be able to say, is this a base transformation? Which basis is this transformation of? V1 or V2? If it's none, then it's not good. So then I will use the conventions, because we're going to have many spaces. I will use the convention that the first index on this vector designates the name of a space. This is the first party. This is the second party. And states within each space would be labeled by second index after comma. So here's an example of the most general quantum mechanical state for two parties, for H1 or V1 cross V2. It's a sum, it's a linear combination of tensor products of individual vectors from individual spaces. And you sum over J until certain number L. Now let's look L equal 1. If L equal 1, it's a direct product of state of one space times another one. And what is this? This is very trivial, because you know that the system is in each subsystem, let's call it S1 and S2, are in definite state. You know where they are, because you can use projection operators, and you can measure things as typical in quantum mechanics, and you will see this is fine. But the interesting thing starts if you go with L equal 2. So it's a state V1 cross V2 for one of them plus another one. And it turns out this is the original Einstein-Podolsky-Rosen state, and it's irreducible to the product state. So as I was saying, this is a product state. This is an unfortunate location, but let me just use a simpler formula here, simpler notation, alpha 1 cross beta 1 plus, so that's one state, but another state would be alpha 1 cross beta 1 plus alpha 2 cross beta 2. So this is this entangled state. This is this entangled state, and the next one is entangled state, and turns out that you can not transform this into that. You have questions? I see you.
First, I understood what this is about.
Disentangled. It's a direct product of states. And of course, if you continue with more spaces, it will be times gamma 1 from the third one. But let's just focus with n equal 2, two spaces. It's a direct product of states. Notice that our space is always tensor product, but states can be sums, because by superposition principle, you must add things up.
Alpha is like spin up.
Pardon?
Alpha is like spin up.
For instance.
Yeah, okay.
So you can think of zeros and ones, or you can think of terms in terms of spin up, spin down. And in fact, those, it's a good question, because those states are called qubits, and I will be using them heavily, qubits, probably some not a very good English here, but that's how the name came to life. And the main point is you cannot transform this state by transformation of spaces, individual spaces, or any combination of thereof, of those, this into that and vice versa. So they belong to different categories. And that's what Einstein started with the whole thing. This is entangled state. And the first one is disentangled.
What do you mean by vice versa?
Regarding what? Right, you cannot transform this into that or this into that. That's the meaning of the word vice versa I'm using.
The first is the same, it's a subset of the second, isn't it?
No, right, but what I'm saying is you cannot apply group. So you cannot say, oh, but maybe that's a bad word. I cannot say alpha 1 goes to alpha 1 prime, which is G1 group, times alpha 1, and then, well, the same would be beta 1, it's the same group. Beta 1 prime equal G1 beta 1. So here's a linear transformation on vectors in the first space and the same for the second. I'm saying apply all transformation you wish, meaning choose all possible general linear groups or their subgroups to this state. You will never ever get this state. Well, unless alpha 2 or beta 2 are 0, but we exclude in those cases. So they belong to different categories. This is disentangled and this is entangled state. Now, the difficulty starts, of course, there are different levels of entanglement. This is the simplest entangled state. But, and that's what EPR state was used. But after EPR discovered their state in 80s or 90s, I forgot exactly, there was another state. I will show how it looked. Well, it's trivial, L equals 3. And it turns out that classes, we can call the one with like CL, but this, I will change notations. There would be C0, C1, C2, depending on L. They do not communicate with each other. They're completely separate. So in mathematical parlance, these are equivalence classes, which separate the whole space of all the space of all sets into equivalence classes, where the things talk to each other within the class, but never between the classes.
Talk to each other, you mean the
By group G.
transformation.
Right. That's the meaning of talking today. Might not be typical meaning, but today.
You're just grading tensor problem.
Right. Trivial problem for mathematicians, but apparently unsolved problem. No, for n equal 2 it's solved. It's trivial. But for n equal 3 it's unsolved, from what I know. And then the question is, what are these CL? So CLs would be the whole set of equivalence classes, and L goes from 0 to some max, let's call it M, and that M is minimum of 2 dimensions, because that's actually rank of an associated matrix. Now, where's the associated matrix, you may ask? Oh, it can be hidden here. If you write V as a sum j from 1 to L, you can write this as a a sum ij. Vij, and then alpha I cross beta j. So here's your matrix V, and M is a rank of that matrix V. So the problem is solved trivially, and notice I never said what was the dimension of spaces V1 and V2. So it's immaterial. And this is a well-known result. What I mean by well-known result, the result that all the set of all equivalence classes are written over here. It's a C0, C1, C2, all the way to Cm, where M is a minimum of 2 dimensions. And again, C0 doesn't talk to C1, C1 doesn't talk to C5, etc. But if you take any state, I should emphasize this again, if you take any state in CL, for any fixed L, and some other state different in the same CL, there always exists a transformation, meaning groups G1 and G2, that bring them together. So it's if and only if. It works both ways. So, well, these are two spaces. And somebody may think, well, this is trivial. And somebody may think, well, we can just quantify this whole entanglement by this number L, which in this case is the smallest number of terms in linear combinations that is required. Peculiar fact is that if you have three spaces, that's not invariant. So what I'm saying here is you take, I'm going to run out of space soon, or height rather. You can take state like alpha 1, beta 1, gamma 1, and then add with alpha 1 prime, well, rather 2, beta 2, gamma 2. And you may think that the number 2 would be invariant. It was for 2 spaces. For 3 spaces, it's not an invariant. What I mean by this is there is a transformation of basis which will turn this into the fellow with either 1 or 3 or whatever number you want. Because remember, these transformations, these are sums, obviously. There are indices on group elements and there are indices on vectors and vectors.
You're changing the basis in the factors or in the tensor product?
No, well, factors, always.
Factors.
Right, always factors. So you can turn for n equal 3, for 3 spaces, the fellow with L equal 2 into L equal 7 if you wish, or any other prescribed in advance number. All right, so how would you approach this problem? So we approach the problem from the point of view, well, let's look at all possibilities and try to apply group transformations and figure out what are the invariants. All right, so, well, that's not needed. Now, I'm going to be skipping things. There is an important point here is that I said that V was a tensor product of all VI's. But in physics, very often we need only specific subspaces of those spaces. Why? For instance, if you have a system of identical particles, you grade these tensor products by the statistics. So if these are bosons, then it has to be a symmetric part of a tensor product, or anti-symmetric for fermions. But what we are solving here, for simplicity, the total tensor product of all spaces, because once you figure out how to do the total, GL of V, then you know how to do the subspaces. It's not trivial, but it's not hard. So we do in the largest possible group, GL of V.
Excuse me, sorry, I am far from this, but I think that the common intuition of entanglement is that when you have 2 systems, right, and you check one system, you immediately impose the state of the other system,
Correct.
regardless how far it is. So
Correct.
Can you try to connect this basic intuition with that formula, just if that's possible?
Well, it's trivial actually, because
It's not trivial for me, sorry.
well, trivial has different meanings. So let's say, where's triviality? Okay, let's choose this state, right? And suppose this is spin up or spin down. And this is on Earth, this is on Moon, far away. Okay, we have in our laboratory access to this spin. We can send it through magnetic field or etc. We can measure that spin.
All right.
Once we measure that spin, suppose it's up.
Okay.
We know that the other one is up because this is the basis for the spin would be then alpha 1 and alpha 2. Alpha 1 is up, alpha 2 is down.
Okay.
We know it was alpha 1 cross beta 1, not beta 2. Therefore, we know what's going on the Moon. Good. Let's take this one. With this one, after we project, these are orthogonal states because this is orthonormal basis, alpha 1, alpha 2, for here on Earth. So once we measure alpha 1, for instance, we know Moon has beta 1, or alpha 2 has beta 2.
Okay.
That's a simple answer of knowing what's going on out of your causal region, out of your light cone,
Okay.
despite the fact there was not enough time for the information to arrive back to us. It's very simple. So, right. Right, one thing I wanted to emphasize very much, because it was already asked a little bit, about the difference of groups. So what I'm doing is I am taking the tensor product of groups, GL, the largest groups acting on spaces V, I am not taking GL of the tensor product of spaces. And if you notice, this group is hugely larger, greatly larger than this one if dimension of spaces goes up. It's factorial product. Well, of course, it's a subgroup,
Block
but...
diagonal.
Pardon?
Block diagonal.
Right.
Well, it's bigger than block diagonals, that's the point.
Well, it's exponentially large because in order to see what's the dimension of this thing, you just multiply 2 to the, so let's see, yeah, you just add things here. You have number of parameters that gives you GL of V1, GL of V2. But in this case, you have to have GL of V1 cross V2. And it's, because it behaves exponentially, this thing blows up. Well, it's much larger. The first line is much larger. And we are not allowed to use the first one because you scramble the whole state. That's my point. You want to do your Rubik's Cube just rows or just columns, not some crazy mixture of elements. So then, well, probably I should skip this stuff. But the thing I will be talking about, well, everybody knows what equivalence class is, but I'll just remind that if you have two states, let's say V1, V prime and V, I guess, right, V prime and V, they are equivalent under relation on V, which is induced by the group, if and only if there exists a group element that connects the two. And of course, it goes the other way because group has inverse element, etc.
Why are you using the group GL, not the unitary group? I think
Because, right, you're asking a valid question because quantum mechanics is interested in unitary transformations. You can do orthogonal transformations if you wish. But it's simpler to do, GL, first answer. Second answer, this is all you need to do. The next step is much simpler. If you just restrict GL to UN or to orthogonal group or symplectic groups, whatever you want. So the object of our study then, once we figure out which states are equivalent to which, so you see, we don't want to find particular state. This would be depending on the basis. We want to find the set of all possible states that are connected by G transformation. Therefore, we're looking for class C of V, which is a collection of all V prime such that they are all equivalent to any given little v under the equivalence imposed by the group G. This should be G probably. And the point then is, once you found the equivalence class C of V, you can find a disjoint set of all equivalence classes. Capital C, this is my capital C here on this formula. The set of all, it's a disjoint set of all equivalence classes. And I use the word disjoint because there is no overlap. Because if there would be overlap, this would be a problem with definition of equivalence class because things will talk to each other across the board, which they don't. There is a wall. All right, so then basically in mathematical language, this can be phrased as we are looking for orbits of a group G, if you wish, or we're looking for the quotient set V by the equivalence relation that we have. But I'm a simple-minded man. I'm not going to use these sophisticated words. So, well, I already mentioned that, and basically what I said before was that there is a one-to-one relations between physics terminology and mathematics terminology, and I mentioned decomposable vectors, which is the product like these. These are decomposable vectors, and they are called disentangled states in physics. And non-decomposable, meaning those that cannot be written in this form, not necessarily those that can be written in this particular form because it's a relevant concept, as I said, called entangled states. And of course, there is a zero vector, which is the vacuum state. But of course, the most important part is to split the structure because this is enormously more complicated than those two classes. And that's our goal. And just to give you idea about, well, I don't know. Well, to give an idea that this problem is difficult, we can estimate dimensions of spaces V and dimensions of group G, and you would see, for instance, that dimension of a big tensor product space go exponentially with a number of spaces, where I see something like log 2 for qubits, but dimension of a group is of order n of dimension of n squared for general linear groups, and less Well, it's still order n squared for unitary groups, etc. So the point is, you are trying to take quotient of v by relation imposed by g, and the conclusion from here is, without going into details, is this is a derivation of it, but the conclusion is there are so many classes that the problem is hopeless. So I could have ended talk here, but and everybody knows this in the field, so what people do, they say, well, if we cannot look at cannot list all equivalence classes, we can look at equivalence classes of equivalence classes. Now, how you define that? Well, you have a certain, maybe that's what, no, actually, that's not what I'm doing now, but I just want to, I'll come back to that. I just want to show how it looks for 3 states. And I use the word qubit, and the qubit means it's a spin-up, spin-down system. So qubit is the collection of 0 and 1, or if you wish, collection of spin-up, spin-down in physical language. So you have an electron that can have spin-up or spin-down. Qubit, 2 states. So it means that dimension of each of the spaces is 2. But our result, which we have, are much broader. We actually solve for arbitrary dimensions. Well, I'll explain what I mean by solved. So then, for instance, of course, you have 3 groups, you have 3 spaces, you have 3 groups, tensor product of those, direct product of those groups, and that's your transformation on the total V by that, so that's trivial. And then you introduce basis coordinates, and the most general element, of course, looks like a triple sum, coordinate, and product of 3 things, just linear algebra. Okay. Then it turns out that this is the full list of all possibilities for 3 qubits. There is nothing to do with 2 spaces, 2 qubits or non-qubits. But with 3 spaces, huge difficulties start, enormous difficulties.
Excuse me. Sorry, may I have the second question? Why it is so that 2 states can be disentangled or simply entangled? Is it not possible that they are like partially entangled in that sense that checking one system, you modify the probability regarding the second system?
Well, the
But
system is
determine-
separated.
Yeah.
You don't modify.
Yeah, but I understand that if they are entangled, you determine the second system
Correct.
checking first. But I think that it can be easily that you not determine, but you, okay, initially regarding the system of the moon, you have some probability distribution, right?
Correct.
And checking the system on the Earth, you can just modify the probability distribution.
But he's collapsing the wave function. I mean, his
I'm
whole
just
model is
measuring.
on
It's a measurement process.
Collapse of the wave function. That's the model he's doing. He's not altering the Hilbert space, but he's collapsing the wave function, the specific
So
probability.
just,
But you could, in principle, have coefficients in front of your.
Correct.
Yeah,
Right.
I mean,
So I would have a
you
probability
model-
of detecting spin up or probability
Yeah.
of detecting spin down, of
Yeah.
course. That's what these coefficients I written here.
That would maybe.
Maybe
correspond
does it
to
help?
What you have in mind.
So there's a probability 40% to detect spin up and 60% to detect spin down. But of course, measurement itself tells you this or that. That's a postulate of quantum mechanics.
This is all post-collapse.
yeah, but I can imagine that something is like,
Well, you could manipulate the state on the Earth, for instance. Once you split them, then you could put the state on the Earth through a polarizer, and it would change the probabilities of the measurement.
yeah.
But that's all before this kicks in.
What Thomas, I think, has in mind that you by measuring on Earth, you may restrict the set of possible states on Moon
Yeah,
with respect to what we did
Well, that's
before.
correct. You just
But
basically.
not restricted to one element set.
Well, if you made a measurement on alpha, you know what it is on beta, as I just said, because you have a coefficient.
The
Well-
same beta that you have on the moon may not be up or down, but it is a simple vector in the Hilbert space locally.
You could add another term here.
To the second line?
Alpha,
yeah.
alpha
Yeah, right,
2,
right.
beta 1.
Well, of course there are cross terms because the matrix doesn't have to be diagonal. This is for diagonal matrix only. Is that the confusion? I've chosen the simplest case because this is actually a canonical form. You can reduce all symmetric diagonal matrices, all symmetric matrices can be diagonalized, and you can put eigenvalues 1 by normalization, so that's a canonical state. Including off-diagonal terms doesn't give you more generality. So turns out this is the full answer for 3 qubits, meaning 3 objects of dimension 2. There is a vacuum state, trivial, v equals 0. There is this entangled state, alpha 1, alpha 2, alpha 3 in the previous terminology. And then there are a set of entangled states, and they are distinguished. There is a type 1. There are 3 different classes in type 1. So let's examine what this is. You take first space, remember the first label means name of space. You take the first space tensor product plus another vector from, again, 1 plus 2. So what I'm saying is you entangle space 1 and 2 and then just flatly multiply by state in space 3. So effectively, you have 3 spaces and only 1 and 2 are entangled in an EPR sense. But the third one isn't disentangled because it just flatly multiplied.
Like 2 strands of a braid.
Exactly. We're going towards basically Buniy rings and stuff like that, but slowly going there. So then, of course, there's a permutation symmetry. So you could have selected 1 and 2 as you did, or 1 and 3. 1 and 3, or 2 and 3, and then whatever left is there. So you have 3 possibilities, but this is just combinatorics. And then there's most interesting states, which were discovered, I would say, in 85, 90, something like this, so-called W state by name of inventors, Woodard, or whatever his name was, and GHZ, 3 fellows. And they showed that there are these states, and let's say maybe GHZ is the easiest. It's a alpha 1, beta 1, gamma 1 plus alpha 2, beta 2, gamma 2. Simple. And this one is not so simple. I will show a graphical representation of this. It will be clearly. And maybe I should show now. Why don't I go to graphical representation, which is some slides away, maybe here. Right. And this is more general. We need to put here d equal 2 because 2 dimension, 2 dimension, 2 dimension. This is general Z for two qubits and any third space of dimension t. And in order to modify d equal to 2, you have to chop the upper 2 cubes from every picture. And then vacuum state has no, so this is the origin where the yellow dot is, or orange. That's an origin. So this is a vacuum because there are none. C1 state, that was the direct product, alpha 1, beta 1, gamma 1. It's represented by this dot. C2, C3, and C4, these were partially entangled states. So let's say, how do you understand this? If this is direction 1 and this is direction 2, then there is entanglement between 1 and 2. And you multiply by 3, trivially, because it's one plane. Think about this as how many different planes you need to cover all of the dots. Well, here you just need one perpendicular to the third direction, means it's a direct product. I mean, it's just producted with the third dimension. But you cannot do the same with one direction or 2 directions because they are, it's a diagonal matrix. If you look from above, this is matrix rank 2. And the same here, the same here. So these are 3 classes of type 1, which I just said. But then W state is this one. And for the symmetry, if it makes you more comfortable, you could add dot here, which means there is an origin, alpha 1, beta 1, gamma 1, but then there is alpha 2, beta 2, gamma 1, because gamma is flatly, well, beta 2, because this is beta direction to the right. And then you add this, and you can add this, but it's actually you don't need to. And then the most complicated GHZ state is 1, 1, 1 plus 2, 2, 2, or 0, 0, 0 plus 1, 1, 1, as people in quantum information would say. And that's where it stops, because for d equal 2, because I said for d equal 2, you have to chop the 2 upper cubes, and there are no these classes. But if d is 2 or 3, 3 or 4, then for 3 you add one state, one class, and for 4 you add another one. And the funny thing is, It doesn't matter if d after 4, how large it is. If d is 75, it's still the same picture. So for all d greater or equal than 4, this is the picture. But now we come back again to where we were. And right, so this is the full list. And just to, again, reinforce, this was a diagonal term, 1, 1, 1 plus 2, 2, 2. And the W state was 3, but you could have added. And turns out it's a complete solution, and people prove it's a complete solution. And actually, I do have a solution. We prove it much, much easier.
Solution to what?
Solution to finding the complete solution of all equivalence classes for 3 qubits. This set. Meaning, you have a space of all possible states, and then you say, can you partition it in such a way that this class talks to itself, this to itself, so they're disjoint, and how many of them are there? Turns out there are 7, including the trivial vacuum state.
Is this
So,
independent of the dimension of the BIs?
no, 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 qubits. The word qubit is, it's qubits. Spin up, spin down, or 0 and 1, or 1 and 2. Now, the problem is, this problem is not solved for non-qubits, meaning higher dimensional spaces. Now, I should have said from the very beginning, we don't do infinite dimensional spaces. So it should be understood we just do finite dimensional, because there are some subtleties, mathematical subtleties as you go from to high dimensional spaces. So these are just 3 qubits, and that's the answer. Nothing else. Well, we pose the question, can we derive this simpler?
So who proved this?
Oh, this was proved by, let's see, do you remember, Tom, who was the author? It's in the past 10 years, probably 15 at most. And I would say this was done by this guy, Chirac. He's a Spanish fellow. Right. So the name of the person is, it's paper by 4. Right, there's one person by, one paper by Dur, Vidal, and Chirac in 2000, so 12 years. And then there is another paper by Verstraete, De Hane, De Moor, Verstrel. I cannot pronounce these Dutch names, if they are. It's 2002. But states themselves, W and H, GHZ, were discovered 5-10 years prior to that, roughly. I have reference in my paper. So the point is, can we go further? What is general picture? Why this thing appear in the way it
You
is?
say that the state like this has been discovered.
What I mean by this, right. Right. What I mean by this is, what's the achievement here? The achievement is people understood that the whole set of all possible states that there exist can be written as a union, I should have written this, as a union of a finite number of equivalence classes. Now,
So the discovery was that this was independent class. This is the
each
essence
of
the
these, right.
discovery.
This belongs to class 1, this belongs to C6, C5, 4, 3, 2, then there is 1, and there is 0. Here are 7 of them. But of course, these are just representative elements, the easiest way to write a state. Of course, I could have put number 13 here and 7 here, and it would be still the same answer. So you look the simplest looking, from some principle, simplest looking, whatever that means, state that belongs to a given class. But the formulation is mathematically tight, because what it says is, well, if you want to know C6 class, that's the last one here, because M is 6, then you take this state and apply G1 cross G2 cross G3 to it until you exhaust all possibilities. Of course, it's continuous, group of continuous parameters, so you have infinite number. But there is nothing else. That's what I mean by discovery. Then the problem is that we would like to solve this problem in all generality, and you would proceed by difficult way, which is just to look at the quotient set. Of course, you could, but that's what we don't do. By look at the quotient set, remember V tilde was V slash tilde by equivalence. So what do? You look at all possible, the most general form for possible states, and you say, well, if I have this equivalence relation, this one doesn't count. This one doesn't count because there is somebody else who is reducible to it. We just need one element per each class, because all others can be found from it. But it's extremely tedious, and I don't know if that's going to succeed at all. Much more efficient way is to actually find some quantities that do not change under the rotation of your cubic Rubik's cube. And these are called invariants. And this is a subject has a long history starting from Hilbert 100 years ago. Again, the field was dormant for 100 years and just recently been resurrected again. Because Hilbert calculated things. Actually, he did have almost classification of 3 qubits, equivalence classes, but it's hidden in all these antique notations. But that's the approach we take. We would like to find some invariants, some quantities that don't change under the transformation of the basis, and then look at the values of those invariants. And if invariants have the same value, that belongs to the same class, but not necessarily. So that's the classes of classes. What I mean is, if invariant for 2 states are the same, they cannot, no, they do belong, no, they do not necessarily belong to the same equivalence class. Because invariants could be just a rough way, too coarse way to distinguish given classes. But it works the other way around. If invariants for 2 different states are different, they must belong to different equivalence classes, because there is no way to bring them by transformation back, because that just contradicts the definition of invariant. And that's the approach we took. And
So actually you look for a complete set of invariants.
right.
Which characterize your...
Well, we don't know the complete set of invariants. That's the problem.
That's the classes, yes.
If we knew that, the problem is solved. But nobody in the world knows this. We know certain invariants, which we construct in the way we construct, and we say, well, we cannot prove it's a complete set, but using our method, there is no any other invariants. But the method might, capture the whole thing. And since I'm only 1/5 or 1/4, I should speed up. And you say no?
You're going to have an entanglement problem here. The end of the lecture will be decorrelated.
And just to skip something, I want to emphasize how difficult it is to find these invariants, because if the number of spaces go like this, 2, 3, 4, 5, and we don't know anything more than that, the number of invariants that we have goes exponentially. And actually 167, we are still working on it. But notice this is very important. When I say number of spaces, 2, 3, 4, 5, I don't say anything about dimensions of spaces. And that's the great power of the method. Because once you figure out what is the number of invariants and how they look, not only their number, but how they look for qubits, you know the answer for any n bits, if you wish. So the analytical expression for invariant do not depend on the dimension of space. It's there, meaning it's generic for any number of dimensions, space. But it's specific to n. Meaning once you solve problem of, let's say, 3 qubits, you essentially have solved the problem of 3 any finite dimensional spaces, tensor product. And, well, essentially because it's important
All
thing.
spaces must have the same dimension.
No,
No.
they don't have to. Any. D1, D2, D3. And then the way I do it, just to squeeze remaining 50 pages in 10 minutes, would be...
So in other words, the strands of the braid can be thick ropes or single lines.
If you wish to think in terms of magnetic field lines, yes.
Yeah, you can mix spin halves, spin 3 halves, and
Arbitrarily. And we have examples of those, which I can just flash in.
Great,
Great speed.
independent of internal structure.
Right, right. And the main method I'm using is just linear algebra, because the whole state V depends on the tensor product, and all I'm doing is basically, I'm just gonna draw one picture, it will become maybe a little bit clearer. So what I'm doing here is, imagine you have 2 spaces again, so it's some matrix, and if I slice like this, if I slice a matrix like this, here are my matrix elements of that matrix, Vij, this is here. This is a vector. I have one vector, I have another vector if I do this, then I have another vector if I do this. This is just for 3 by 3. So I have different vectors. And finding the entanglement information is actually for 2 spaces or for matrix is equivalent to finding a rank of that matrix. I already touched on that. But the main problem, well, of course you can do the same with rows, but we know the theorem, linear algebra, rank row and column row are the same. The difficulty is the following. What do you do with a cube? How are you going to diagonalize your cube? Unsolved problem. It's actually impossible to diagonalize the cube in a way, just like by Gaussian elimination here. You cannot eliminate everything except the main diagonal. There are restrictions. And this is precisely, it's unsolved mathematical problem as far as I know, and this is precisely what this entanglement is about. When you slice, you select you select matrix, two-dimensional subspace, and then you can do things. But things don't agree on different slices. If you can do diagonalization on each individual slice, but they won't agree. Ranks would be different. And things won't go. You would like to have just one guy per each slice in order to have a main diagonal. But you won't in the most general case. In some cases, you will. So then the point is that you want to do the best you can do, meaning there are some constraints. And those constraints are precisely entanglement invariants that we have, because we construct them by the following method. We choose our plane and 3 space, and then we project, we have a map from two-dimensional plane on a dual line, which is orthogonal to it. And the map is given somewhere there, but I don't want to bore you with details. But the main point is you take linear maps from 2 space to a complementary space, one-dimensional for n equal 3 in this case. And if you have a linear map, there is invariant property of maps associated with them, kernels and images, and you take dimension of that kernel, for instance, or dimension of the image, and that's your invariant, because dimension of a kernel, which is nullity, does not depend, or dimension of image, which is rank, does not depend on the choice of basis. That's the main argument. But the combinatorics comes in. You need to slice in all possible ways. Some of these slices are dependent. So for instance, if you chose in the plane 1, 2 and map 1, 2 to space 3, that is dual, which means the same as mapping from 3 to 1, 2, just like in rows and columns. But mapping from 1, 2 to 3 is different from mapping from 1, 3 to 2, because these are different objects. And then you consider all these spaces, and again, well, these are how maps are written. This is standard kernels, etc. And main point is that you need combinatorially choose all possibilities. For the 3, it's just 6, but it's a pairs of 3. They're equivalent. And once you do that, you calculate the kernels, which are invariant objects of these maps, and then you calculate their dimensions. But there's one essential step. If you would do this, let's say, for qubits, you will be able to see those trivial classes which I showed before, but you won't be able to see the class W, the class GHZ, because class G, HZ, and W are tricky. They are not about linking. Think about matrices like linking loops, like hop links. You link the 2, and the third is free, and you do permutation. But how about those things which are linked all the way together? That's your W state. Now, where's Borromean rings? It's a GHZ state. They are pairwise unlinked, and the whole configuration is linked. That's visual picture. It's actually, you can put pretty good math to prove this concept. Because, you know, kernels of linear maps, it's a topological property. They are topological invariants, but they're so simple then it's not even worth talking about homology and etc. So the main point is you look at all the invariants and skipping all this stuff. This is just explicit, and this is actually how to do for 3 qubits. You will find, this is the complete analysis, you just write system of linear equations and solve them and say, okay, this is how you do it, and you will find, equations are not harder than this, and you will find this table. So this table lists C0 through C6. This is 3 qubits, 4 columns. First 4 columns correspond K1, K2, K3, and this funny invariant that talks about how 3 spaces talk to each other shows the values of invariants, and the last column shows representative state. And this is our way of doing. We did it a year ago, and we got exactly the same answer as people did through many years finding this full classification. It's a full classification. Then the point is, how do you go further? Because basically, this is where the standard results, known results end. Well, they go a little further. So let me show where the results end. So what is written here, no, that's the wrong table, this one. what is written here is a set of dimensions, D. So 2, 2, 2 is 3 qubits. This is all for 3 spaces. And number of classes is 7. So people knew this before us. They knew the second line too, 9 classes. But they did not know, well, there was a conjecture that this is true. That for D greater equal than 4, it's 10. But remember, I showed this picture, well, picture doesn't prove, that it's always 10, well, from 0 till 9. 10 classes, and it's for any D greater than 4, it doesn't change. So the point is, we proved this.
So you previously said you didn't have a complete invariant, but now you're actually telling me the number of classes based on your invariant.
What I mean is, right, we use in our method, linear algebra method, there are no any other invariants of this kind, I mean discrete invariant, etc. And it's maybe coincidence that it's actually number of classes corresponds to what other people did. But we're not doing something very different from them. We also group classes into classes because it's a hopeless problem due to exponential increase.
So, but these are the number of your classes.
Correct.
The
And
classes of your invariants.
right, and that's this number, well, next one. And this number 7 is the same for other people, agrees with that. The third line here was conjecture, we actually proven it, quite elementary. So then you say, well, what happens if you have 1 qubit and 2 tetrads? I guess that's the name, right?
Spin one.
Spin ones, right. With dimension 3, 3, and then it's getting harder and harder naming them, of course. But these are number of classes you got. Well, we got. So below this line, nothing was n bits. Below this line, nothing was known, except for maybe conjecture for 2, 3, 3. But no conjectures were known for all this stuff. We got number of classes, and we actually get for each of these class representative element. Well, you say, how did we on Earth did anything like 262 classes? Yes, it's Mathematica, but following standard linear algebra problem. But we did few of these first ones by hand. But this is just using.
But you said a moment ago that nothing depends on the dimension of this set space.
Right.
Everything depends here on the dimension of the
Right.
space.
What I said, correct. What I said was how the invariant is written doesn't depend. So expression for the invariant doesn't depend on the dimension of space. The value that invariant can take does depend. And we are listing here the number of invariants. Number of classes. Right, right. Okay, let me just back up and say it again. Here they are. Let me see. No, maybe I do have them listed. Yeah, I think
I
it's.
understand that invariance is a somewhat separate problem from the number of classes, because you can, if you're diligent, you can just count these classes.
Well, that's what we did.
Without inventing an invariant.
That's what we did.
Correct?
Right, but first we had to invent invariants. So what I'm saying is, let's have a look at 3 spaces. For 3 spaces, there are 4 invariants in our classification. There's nothing more. So what do I mean by this? I mean, take dimension 1, xy, x1, x2, x3 in here,
Yeah.
select as a special dimension, and then project on 2, 3, complementary 1, etc. So that's the meaning of this 1. The meaning of this 2 and 3 are equivalent. Then if you choose 2, 3, this would be just dual map, and it has the same nullity, so the number invariant is the same. Now, Q4 is the one, like Borromean range, then talk how 1, 2, 1, 3, and 2, 3 intersection. Now, when I say invariants, here they are. Invariant NQ1 of V, it's a nullity of the map associated with this combinatorial choice. Then N2, or NQ2 I call it, sorry. It's the nullity, it's the invariant associated with this choice, and with this one. And with NQ4, but these are particular values. But the invariants are defined as a dimension of linear map. Doesn't matter how dimensional space is, how much dimensional space is. But the values that invariant can take, of course, enumerates up to the maximum number. Okay? So then of course, as I said, these are all novel results, and I said we do them using them standard linear algebra packages in Mathematica, but the principle is simple. And then we have also representative elements, and we check this with various classifications known in literature, and I mean classification meaning this is a representative element. Well, do it right. Then, important thing is to compare this with Hilbert invariants. And Hilbert invariants are continuous, and if you can see, they're nightmare. Well, not here, but nightmare starts later. Maybe, well, nightmare would be a few pages away. And turns out these are our classification. These are Hilbert invariants, classical invariants so-called. They are continuous. And turns out there's one-to-one map between our classes and the set of zero invariants, zero values of Hilbert invariants. Coincidentally, there are 4 classical Hilbert invariants as well, and these are our classes. And as you can see, well, it's not one-to-one, I just lied, but you can remove the first one because it's a trivial class, and after that you have one-to-one correspondence. Whether they are, it's basically you imagine something, lower dimensional object living in high dimension, and whether you cross the surface or surfaces cross, etc. So that's a relation. And then, well, since I'm out of time, let me just show that actually we have, let's say, this is the case for dimension 2, 3, and arbitrary d. There are 26 of those, 25 plus 1, and for any d greater or equal than 6. It's always d greater or equal than product of the other 2. And then these are pictures that represent those things, showing, you can see a little nice geometry and topology here. And then absolutely unknown results are for 4 qubits or 4 spaces. And there are 19 invariants now. They are basically showing, okay, you can choose space 1, 2, or 3, or 4. That's one choice. But then you can choose 4 possibilities for pairwise among each class of 3, like Buniy means. But then there's more complicated. You do 2 and then 2 of 3s. And then you finally, no, then you do 1 of 3s and 3 of 2s. And finally, the most complicated, there are 4 triples intersecting. So it's correspond to the Brownian link now, not Buniy, it's the next one. It's a higher order topological invariant. And then, of course, here's our values with the with the values of invariants. Well, there are 72, well, 82. 82 classes. This is unknown literature. What is known, people have 25, or what are 25? No, they have 9 classes, but there's a symmetry here. So if we reduce these 82 to permutations, we have 25 independent classes if you ignore changing x1 with x2. I mean, v1 with v2, because that's, well, provided they are the same dimension, which they are for qubits. So to conclude, almost, so these are states just for beginning of them, and then Hilbert invariants are nightmare for the higher ones, just to give you a flavor. The first h1 is easy, but then h2 is this determinant, h3 is easy, h4, but h5 is a determinant 3 by 3 where each element is listed here. And you can see this is the full 9 entries of the matrix. And then
hyperdeterminants.
These are hyperdeterminants. These are Cayley hyperdeterminants, a famous thing from 1890 or something, whenever Lord Kelvin, was it Lord Kelvin, right? No, Cayley, not Lord Kelvin, right. Did it, so...
What is hyperdeterminant?
It's like a determinant of a cube. That's what I was talking about. So there's an invariant quantity associated with a 3-dimensional matrix, if you wish.
Do you have hyperdeterminants for 4-dimensional?
Well, people do have, but the current knowledge stops at 5. Probably for 5 they know, but the problem is they have hyperdeterminants only for 2 by 2 by 2, for qubits. They don't have for 3 by 3 by 3, for instance. But the problem is we don't need those. Our elements, our quantities that we have, kind of circumvent this problem of finding hyperdeterminants. This is an extremely difficult mathematical problem.
Sort of your classification is probably a different classification
Yes.
than Hilbert's.
Correct.
Yours is based on the group GL, and probably...
No, that's not the main difference. The main difference is we have discrete invariants versus continuous invariants. Remember the table I showed you, 0 and non-zero values of Hilbert, continuous invariants correspond to our classification based on discrete invariants.
Do you prove that you have all possible invariants for some in some scheme, in the GL scheme, for instance?
Whether we prove if we have all invariants, we have all invariants which are possible to get through the linear maps, through our construction. But we don't prove that any invariant can be written as a function of our invariants. We don't do that. We don't know how to do that. And there are some interesting relations between Hilbert invariants, etc. And here is the way to show how Hilbert invariants, well, they are sufficient to distinguish different classes. So these are values of Hilbert invariants for 4 qubits, and these are classes in our case that correspond to this. So for first line is basically 3 lines here. But if you look at the values of Hilbert invariants, this is an adequate method of finding equivalence classes or distinguishing different entangled states. But if you look only on value of zeros or non-zeros, this is not sufficient because, as you can see, most of them are not one-to-one. There are multiple classes that correspond to given values 0, non-zero of Hilbert invariants. But the problem is, Hilbert invariants are good here only for 2-dimensional spaces. But our invariants work for arbitrary dimensional spaces, and we don't stop at n equal 4. We do for any n. So then finally, to conclude, I would like to draw the distinction between the known methods and what we do. So in old method, we have very simple definition of invariants, meaning like Hilbert invariants. You just find them, but the problem is to find their values. Find values and then distinguish states that belong to different classes, because they would have different values of invariant. In our case, we have both simplicity in definition and in calculations. These are just ranks of various linear maps, linear algebra. All right. Then, of course, the old method is more powerful in a way that it's used well-established geometric invariants, and there are various books written on this, obviously. This disadvantage of this one, this is new, but maybe that's advantage. And what we did show, which is partial answer to your question just again, that there's one-to-one correspondence between classes and classes of linear maps. What we didn't prove that there are invariants that we capture all possible equivalence classes. We did not prove that. Some things might have escaped, but what we know for sure, there is at least this number of classes, not less. Because other people, for comparison, for 4 qubits, they have number 9 of classes. We have 25. Well, I showed you 82, but by permutations, you can reduce to 25. So we have vastly more. And we actually show how they originate topologically. So then, all results we found so far absolutely agree or supersedes, meaning they are never smaller than the known results. So our results are always stronger or equivalent to the previous results. There's not a single violation when we didn't get a weaker result. And of course, there is a vast amount of new results, as I showed you. In that table, only first 2 or 3 columns were covered by previous literature, but we had enormous, and it's actually not everything included in the table. And what is interesting for me in particular, for us in particular, is to try to see how this ties up in topological properties of associated, closed associated links, because we started with these Borromeans. And what I just want to just mention where we're going with this. So we still don't have analytic formulas for arbitrary Ds. We have numerical results for values of invariants, not for the invariants themselves. We know how to write them. But we don't have an analytical formula, but we believe we are close to that. And then we would like to restrict, because the thing goes exponentially, we would like to restrict our dimensions to 2 for qubits for the purposes of quantum computation. That's what people are interested. 2 qubits, but then do for higher n's. Well, we did for 4. We're working on 5 right now. And there are physical applications to that, which I didn't touch, and on some of these I worked previously, which is a relation between this approach and a continuous measure of entanglement, like entanglement entropy, and there are others. That's leads to black hole entropy. That's the subject I worked on. It turns out that you can write black hole entropy as an entanglement entropy, and you can explain this new phenomenon, which is recent discovery, the largest discovery in theoretical physics, holography, which basically the world actually is lower dimensional than we think it is. But this is too complicated concept to explain right now. And these ADS CFT, this is big discovery of recent 10 years in theoretical physics. And you can look on relation between our discrete as opposed to continuous entanglement entropy discrete measures to some topological charges, because it's well known that, let's say, black holes have a discrete quantum numbers, which quantum number means they are invariants. And we can ask ourselves, what is the relation between invariants we have to these quantum charges? And if we do have, then we can start writing actuals on physics with these things. Thank you for your attention.
I guess we're pretty severely over time, but maybe one or
Sorry
two
for this.
questions.
I'd like to ask the number of the equivalent class. So
Number of what?
equivalent class. You have some
Table?
table, yes.
Which one you want me to show?
About the 50. Oops, go back.
Here.
Yes,
This one?
Yes, I feel very regular because the difference. For example, so 10 minus 9 is 1, so 26 minus.
Oh yeah,
minus
that's a
1
pattern.
is 7.
Yeah, you are absolutely observant.
1 to 7.
That's a pattern.
1 3.
It's always
Do you
true.
have some variation?
Yes, there are these rules that it's always 262, 261, you see, and then it goes by 3, and it's the same story here by 1, and then, well, here by 2 because there's a restriction. We have all those various patterns, and they are partially written somewhere here, but not completely. We have just, phenomenological observations that this is true, but we didn't prove. Because remember, this is generated by computer code, well, vast majority of this, but it's a complete set, because we just enumerate all possible invariants. But yes, there are these regularities in this pattern.
So this also holds in general case, so n is 3 or 4.
Well, I don't know if it holds, I don't want to lie. But what I do know holds is the pattern with these pictures, which means if you have two spaces d1, d2, then you need to look only d3 less equal than d1 times d2. So the height of these cubes is always a product of, so here, but remember, for each of these, this is 2, although it looks like 1 cube because you count number of on intersections, like you're playing Go instead of chess. But this is 2 times 2, so you go all the way up to 4. There's nothing ever more than that. So that's a general pattern, we proved that. But there are these very subtle patterns in the table, as you notice, and we observed some of them, we proved some of them. I think we proved this one, that this difference is always 1 in the last one. Before you reach the saturation, the step is 1. But I don't think we have a proof of previous.
Maybe one more question?
Unfair question about physics. Go to the second line on the blackboard.
On the
Your
whiteboard?
V prime or V tilde.
Right,
Is the entangled state.
right. EPR state.
It all depends. I mean, the statement that we learn what happens on the moon instantaneously depends on the fact that we must know in advance that the two parts together are in that state.
Well, because we prepared it on Earth, and then we send the party 2 away.
And the question is, what are the physical circumstances that realize that situation that are of interest?
It's a very deep question.
Yeah, I know it's an unfair question, but...
Well, I didn't say unfair. It is unfair, true. Regarding this talk, people are working on this since Einstein's paper. You know, what is the practical application of entanglement? And, for instance, quantum computation is one of them. There is a huge discovery was made by Peter Shaw, for instance. I don't know if you're familiar, but mathematicians from MIT, who proved that you can crack the RSA or whatever encoding that we are all using our credit cards can be cracked by quantum computations, although it's protected by classical computer. What I mean by protected versus can be cracked is that it takes enormously large amount of computations to figure out your PIN number, essentially, well, encrypted message, because you have to factor the prime
It's
numbers.
easier to ask.
Right. So, right. It's not only PIN number, it's encrypting of the whole information you send to a bank. But in order to do, for instance, for a typical 100 or 200 digits not prime number, composite number, which is the product of 200 digits, let's say prime numbers, it takes on average the age of the universe to factor, with the current speed, to factor that number. Now with what Peter Shaw showed, that if you use quantum computer, which is based on entanglement, just strongly based, you can do it so fast that people start thinking about, insecurity of standard encryption, and that's why they do all other things. But quantum computer, as we speak, is not built yet. But that would be one application.
There was the experiment of aspect, Alan Aspect.
Familiar name, right?
Maybe, I think he's done some experimental test of those Bell inequalities. So that may be connected to entanglement.
Well, I didn't touch anything on Bell inequalities. There is some controversy regarding that, so I actually don't know much about that, so I don't want to give you your own impression. But the other comment I wanted to make regarding this was that I said the quantum computer is not built yet. That's not completely a correct statement, because if you call something that has 100 gates a computer, something, 100, whatever they call AND and OR gates, it's a computer. Yes, people did build something with 100 qubits, but not anything even close to this computer.
Entangled 100 qubits.
Pardon?
Entangled 100 qubits, you say,
No, just qubits.
which are not entangled.
Well, you entangle them because you create a quantum state. And the main reason why this Peter Shaw result on quantum decryption is so well known is it's exponentially faster than classical computer. And the main reason for that is precisely here. When you deal with classical qubits, it's either 0 or 1. But when you deal with quantum qubits, you deal with a continuum of coefficients in front of it. So this matrix V. And that enormously increases your power of doing things. So essentially, a quantum computer differs from classical computer by saying, I don't need to model things in zeros and ones, which looks like an insane idea, right? Because if it's not 0 and 1, what is it? What's the probability that you will add numbers correctly, you will multiply? People know how to deal with things like this. But it's still a work in progress, and probably for the next 50 years, people are going to work on it.
Well, we should thank Roman one more time.